This video is part 1 of a lecture from section 7.4, Singular Value Decomposition, for Math 311, a course in linear algebra at Western Illinois University. Okay, so this is our last topic of this course, but it's probably one of the most important ones, especially if you're planning on going into engineering. Because this is a topic actually I didn't learn in my first linear algebra course, but it's very important. And what this is a sort of a generalization of diagonalizing matrices. Okay, we know that if we have a square matrix, if conditions are right, we can diagonalize it. Right, that means we can if A is an n by n matrix, then if the conditions are right, we can find an invertible matrix P such that A P inverse A P is diagonal, right? Okay. Now this does not always happen for all square matrices, right? There are a whole bunch of conditions, in particular the algebraic multiplicities and the eigenvalues have to equal their geometric multiplicities, but if this happens, it's kind of nice. Now, it turns out what happens if we have a non-square matrix? Well, believe it or not, we can actually do something similar. Okay, and the nice thing about this is this will work for any matrix, not just square matrices. This generalization. Okay, so it's going to be a little intense. I have most of the theory written out, so let's go into this. Okay, so throughout this topic, A is going to be an m by n matrix, and we know that if we multiply A transpose times A, that will be n by n, and it will be symmetric, and because of it's symmetric, it's orthogonally diagonalizable, which means that we can find an orthogonal matrix V, okay, such that this is true, such that V transpose times A transpose A times V is equal to this diagonal matrix. It's an n by n diagonal matrix, right? Where the lambdas are just the eigenvalues of A transpose A. And as I said, V is some orthogonal matrix, an n by n orthogonal matrix, and we're going to denote the column vectors by V1 through Vn. Okay, and as I said, these are really just the eigenvectors of A transpose A, where A transpose A VI is always equal to lambda I times VI. Okay. Now, so this is so far nothing new, right? Because in previous lectures or topics we used Q as this matrix, but we're going to use V. It doesn't really matter what letter we call them. Okay. Now we already know is because this A transpose A is symmetric and real. Okay, we're assuming everything, all the entries are real here. The eigenvalues will be real, but they're also going to be, in this case, there will also be non-negative. So we're going to prove this first fact that, in fact, every lambda I is greater or equal to 0, and in fact, the square of the length of AVI is equal to lambda I for all I. Okay, so that's something a little new. So why is that true? Well, if we start off with, again, the consequence of having an eigenvalue, then because VI is the eigenvalue for lambda I, we have A transpose A VI is equal to lambda VI. And then we're going to multiply on the left by the transpose of VI. So remember, this is a row vector now. All right, so we have VI transpose times both sides. And then by the properties of transpose, we know that this thing right here can be written as the transpose of AVI. And on the other hand, or on this side, we know lambda I is just a real number, so we can pull it out. We can pull these scalars out wherever we want. So we're going to pull this out in front, and we get VI transpose times VI. But remember, when you take a column vector and multiply its transpose by a column vector, it's the same thing as taking the dot product. And because when you take the dot product with itself, you get the square of the length. So this, in fact, is going to be the length of AVI squared, and this is the length of VI squared. And because VI is a Well, it's an eigenvector, so of course this is not 0. But in fact, it's also because V is an orthogonal matrix, these vectors are orthogonal, which means the length of all these vectors is 1. So that's why we know that 1 squared is 1. So this is 1. And anything squared, any real number squared, is going to be greater than or equal to 0. So it has to be that lambda I has to be greater than or equal to 0. Okay, so that's why all these eigenvalues in this case are non-negative. Okay, so we can rearrange the indices as the order of the eigenvalues if necessary, and we're going to assume that the first R values are strictly the first R eigenvalues are strictly positive, and everything else is 0. All the other eigenvalues are 0. Now, we're not saying that one of the eigenvalues has to be 0. It might be that they're all positive, okay, in which case R is equal to n, okay? But we're going to rewrite, that's what the significance of R is, okay? And then we're going to define sigma I to be the square root of lambda I, which we can do because we now know that lambda I is non-negative, okay? So, and then we have a special name for these sigmas, sigma 1, sigma 2, up to sigma n. These are the singular values, called the singular values of A. Okay, move this up here so you can see. Sorry about that. And again, some of these singular values might be 0, depending on what R is. And we also note that the size of each vector, AVI, is equal to sigma I for I equals 1 through n. And that just comes from this up here. We're just taking the square root of both sides, okay, of this equation. And in particular, the AVI is going to be 0 for I equals R plus 1 through n because the lambda, the eigenvalues are 0, okay? So that's why that's true. All right, so so these VIs are, we've dealt with the VIs before. Now what we're going to do is define some more vectors. Here. We're going to define we're going to define our vectors, and we're going to call them U sub I. And we're just going to define that to be 1 over sigma I times AVI, okay, for I equals 1 to R. Now we stop at R because for all the other for all the other values of I, sigma I is 0, and we can't divide by 0. Okay, so we're talking about R vectors like this. All right. Now, if we take just these R vectors, turns out, for our second fact, that this set, U1 through UR, is an orthonormal set of column vectors in Rm. Okay, and that, by the way, the hardest part about this whole talk is going to be just keeping track of the dimensions of everything. UI is in Rm, first of all, because remember, A is an m by n matrix, and Vi is a column vector in Rn, so it's n by 1. So the result is m by 1. So it's a column vector in Rm. Okay. So why is it orthonormal? Well, we just have to show that we're going to take the dot product. We take the dot product of ui and uj, and we're just going to see that's either 0 or 1. So remember the dot product, as I said on the last slide, that's the same thing as just taking the transpose of one vector, multiplying it by the column vector. So this is just dot product of ui and uj is this, and if we substitute, this is just the definition of the ui and uj. And once again, we can use the fact that this 1 over sigma I and 1 over sigma j, those are just real numbers, so they're scalars, so we can just pull them out in front. And what we're left with is then we take, so we have vi transpose A vj, and remember A transpose A vj, this is going to be, remember, this is just going to be equal to lambda j vj, because vj is an eigenvector of A transpose A, and sigma j, or I'm sorry, lambda j is just the same thing as sigma j squared Vj. Okay, so this just comes from the fact that Vj is the eigenvector and the eigenvalue is sigma j squared. So that's how we get this. And sigma j squared is just another scalar, so we can pull that out here. And one of the sigma j's cancel. The sigma j's cancel because they're non-zero. And remember that Vi and Vj are going to be orthogonal to each other if I is not j, equal to j, and it's going to be equal to 1, because we already know if I equals j, because we know that this is the vi's are going to be orthonormal, right? And we know that because the big matrix V is orthogonal. Okay, so what happens is, so this is either going to, if I equals j, of course, this just becomes 1, and this is 1, so we get 1, and if I is not j, then that means that this is 0, so we get 0 here. Okay, so that shows that this is, in fact, an orthonormal set of vectors. Okay, now, we can extend this to an orthogonal orthogonal basis of Rm via Gram-Schmidt. Okay, now this is the one tricky part of this this whole process, and sometimes you might have to extend it. Sometimes if R is equal to M, then there's no problem. But we can extend this by using Gram-Schmidt. Now the hard part will be if you want to use Gram-Schmidt, you need to find some vectors that are outside the span of this subspace, and that might be a little hard to do. In the examples and the homework that you'll be doing, that won't be an issue. So we'll don't worry about that too much. But just know that if you have faith in the Gram-Schmidt algorithm, this can be done. So you can get this orthonormal basis of Rm, U1 through Um, and then these are column vectors. And so we can put them together and form this matrix U, and then the U will be an orthogonal M by M matrix. Okay, so this is an M by M matrix. Okay, and now that's all we need to find the magic of the singular value decomposition. If we first we're going to compute A times V. Well, that's just going to be the columns of AV are just going to be in the form of AVI. And remember from these columns right here, AVR plus 1 through AVN, these are all going to be 0. We already know that. And these, because the V1 through VR, these are eigenvectors, these can be replaced with sigma U times U. I should say, well, we'll go this through step by step here. Okay, so we said already know that these are zeros, right? Okay, and then from the definition of UI up here, notice that this means that sigma I, we can multiply both sides by sigma I, and so sigma I UI is going to be AVI, right? So that's how we get this next step right here. All right, and then comes this amazing little trick here that we can actually write this as our matrix U, which is the U1 through UM, times this matrix, this new matrix we're defining as sigma, and it's not quite a diagonal. It consists of basically all the only part of the diagonal consists of the sigma 1 through sigma r, and then everything else is 0. Okay, so it's not quite a diagonal. If r is equal to if r is equal to n, then this would be diagonal. But we can just go. We can always describe it this way. So this is sigma, and maybe we should just keep in mind here that U is M by N, or M by M, and that the sigma is in fact M by N. Okay. Okay. Now, so this is true, And then because V is orthogonal, V inverse is the same as V transpose, and we can multiply on the right both sides by V transpose, and then these V and V transpose cancel, and we get A is equal to U sigma V transpose. And then this, in fact, is the singular value decomposition of A. Okay, so that brings us to the main result of this whole section. The singular value decomposition of A, where A can be written as an M by M orthogonal matrix times our matrix sigma times the transpose of an orthogonal N by N matrix, and call that V. Okay, so A is equal to U sigma V transpose, where U is an N by N orthogonal matrix, V is an N by N orthogonal matrix, and sigma is defined this way. Okay, so this is kind of like the analogy to diagonalization. And again, the nice thing about this is this works for any matrix A. It doesn't have to be square. One thing we should just state to get out of the way is that why are we using the letter R to denote the number of non-zero eigenvalues of A transpose A? Well, because R is in fact the rank of A. And the reason for that is the rank of A, A is equal to U sigma V transpose. And remember that U and V transpose are both invertible matrices, which means they're products of elementary matrices. Multiplying by an invertible matrix on either side does not affect the rank. So that's why the rank of U sigma V transpose is equal to the rank of sigma V transpose, and then that's equal to the rank of sigma. And you can see that this sigma is already in reduced row echelon form, and the total number of non-zero rows is exactly R. So that's the rank of A. So that's an important thing to keep in mind. Okay. Now there is another form of this. We can actually go a little further than this, of course, and this is where things get a little. You really need to keep track of the dimensions of this. So we're saying is U consists of all the column vectors U1 through UM, and V consists of all the column vectors V1 through Vn, so V transpose consists of all these row vectors V1 transpose through Vn transpose. All right, and what we're going to do is I'm going to partition these matrices here, matrices into submatrices. I want to put a little matrix here. And we're just going to let the A1 be this submatrix consisting of U1 through UR. A2 consists of the column vectors UR plus 1 through UM. We're going to define matrices C1 and C2, where C1 consists of these first R rows, and C2 consists of the other rows. And we're going to call this diagonal matrix here sigma 1 through sigma R. We're going to just call that B. And if you go through check the dimensions here, it does make sense. If you multiply things out, this in fact just becomes A1, B, C1. And let's just make sure that this works out okay. What's the dimensions of this? Well, here we have M rows and R columns, so this is M by R. B is R by R. And C1, we have C1. This is we have R rows here, and the number of columns. The number of columns is the length of VI transpose, and because VI is in Rn, then the length is n. Okay, so this in fact is an M by N matrix, and in fact this is A1, B, C1. And you can see the role of the zeros plays a role if you just kind of multiply stuff out here. Like for example, if you take take a row of this matrix and a column of this from here, we can see that the only thing that plays any role is the A1 and the B, and when you get down to 0, you get all zeros. So that's what happens. So as a result, what we get is A1 is in fact this matrix, B is this matrix, and C1 is this matrix. And we can multiply these together. This is just a diagonal matrix, so we're just multiplying these vectors by sigma, the sigmas. And if you could break this, you can break this matrix up as, this first column plus all zeros plus another matrix where you have all 0 columns except the second column, which is sigma 2, u2, and so on. And if you do the calculations, the zeros cause a lot of things to go away, and what we get is this. We get that when you compute this, the only non-zero term is sigma 1 u1 v1 transpose. Here you get sigma 2 u2 v2 transpose, and keep going until sigma r ur vr transpose. And this is called the outer product of the singular value decomposition of A. Just keep in mind that these in fact are matrices. These are because remember, like ui vi transpose, once again, ui is a column vector. This is m by 1, and this is 1 by n. This is a row vector, right? So this in fact is an m by n matrix. Okay. So it does work out. Okay, so that's the outer product form of the singular value decomposition of A, and we can use that in our next when we're actually using A to define the transformation of this. So a transformation of from R n to Rm. So moving on to the next slide here. So if X is just an arbitrary column vector, x1 through xn, and this should be an n here, okay, if there's any doubt. Then the product AX, of course, is going to be an Rm, right? Because again, this is m by 1, and this is 1 by n, right? Okay. So, and as you can see, the phone's ringing, so I am going to pause right now. Okay, I'm back, hopefully. Great. Sorry about that. Live, that's how things are. So, yeah, so AX, AX is, I'm sorry, this X should be, this is actually, well, this should be n by, this is n by n, and this is n by 1. Okay, so the result is in Rm. So you already knew that, I hope. Okay, now if we apply the outer form decomposition to the outer form decomposition to A, okay, so this is just from the last slide, and we multiply by X on the left, we get, or on the right, we get this. We just distribute the X, and now we can do some rearranging on each term, and the reason for that is if we look at these terms, V1 transpose times X and VR transpose times X, this in fact is a 1 by 1 matrix, right? Because VI is 1 row and n columns, and n is n rows and 1 column, right? So this is a 1 by 1 matrix. So it can essentially be treated as a scalar, a real number. Okay, so what we can do is we can pull these over here on the other side of the UR, because remember, and sigma is a scalar quantity as well. So AX is just going to be some number times U1 plus some number times U2 plus dot 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 plus some number times UR. Okay, when where this number, we can call this number YI, where YI is defined as sigma I times VI transpose times X. Okay, and notice that we can divide both sides by sigma I, again because sigma I is not 0. Okay, we're just working up to sigma R, so everything's cool. So we get YI divided by sigma I is VI transpose times X. All right, and then what we have now what we have is AX is just written as a linear combination of the U1 through URs. Now remember the U's in general, the U1 through UM is going to be a basis for RM. So that's going to kind of be a big deal. By the way, interestingly enough, you can see that this will also show that the rank of A is going to be has to be R, because this really corresponds to all the linear combinations, of the columns of A. But this has a particularly nice consequence, because now if we just note that take the orthogonal matrix V and take its transpose, V transpose X is going to be this, and what this comes out to be is that this is going to be a column vector, but the entries are just going to be the dot product of VI transpose and X, okay, or VI and X. So we get this, which again we already know these are scalars. So V transpose X is this vector. Now we're going to in the case that's going to be helpful, because in the case if we restrict our vectors X to be unit vectors, that is, if the length of X is going to be equal to 1, then the length of V transpose X is also equal to 1, because V is orthogonal, so V transpose is also orthogonal. And that means that this length of this vector is 1. So that means if we take the squares of all these components and add them together, that's going to be equal to 1. Okay, and there should be a 2 here. Shame on me. And then if we substitute in, replace, VI, here, VI transpose X with Y over sigma I, we get this. So, okay, now in this case, again, we have, this of course only holds for I, this only holds for I equals 1 through R, right? Okay, so this, we can substitute for the first R terms here. We can replace VI transpose X with Y sub I divided by sigma I, but then we have some other stuff. But this other stuff is going to be positive because they're all squares of real numbers. So we get that Y1 over sigma 1 squared plus dot 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 plus YR divided by sigma R squared plus something positive is equal to 1. And what we've proven here is that this big theorem is that if X is a unit vector, that AX, and if AX is written as a linear combination of the U1 through URs, then the R-tuple Y1 through YR is on the interior of a certain ellipsoid in Rm if R is less than M, and this R-tuple is on the surface of an ellipsoid Rm if R is equal to N. Okay, and by these ellipsoids, remember what those are. In Rm, we have where you have one variable squared over a constant squared, plus another variable squared over a constant squared, okay, and so on. And you set that equal to 1. That is an ellipsoid, okay. And in fact, that is that's what we have here, because we said that this obviously implies that this has to be less than or equal to 1. Okay, so that's what we get here. And again, this is just y1 squared over sigma 1 squared plus dot 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 plus yr squared over sigma r squared is less than or equal to 1. But if we take if we have equality here, this defines an ellipsoid in Rm So this is going, so that's that's why this happens. So yeah, and then if then in this case, in the case where r is equal to n, then this is just this, all these terms, this is just 0, and we have equality here, and we get this. Okay, so this gives you kind of an idea, in particular, what basically is going on here is, I mean, let's say if we take the, if we're in R3, let's say, you know, our matrix is 3 by 2 or 2 by 3, something like that. Then that means that we're going to have, you know, if we take any point on the unit sphere, that means we're going to have a, there's some after we do a change of coordinates, the result will be an ellipsoid, an ellipse in R2. Okay, so every ellipse in R2 is going to be in this form, and so this will be, so any point on this ellipse is going to be sent to, you know, somewhere inside this ellipse, right now in R2. Okay, all right. So there's a lot of stuff we have to, a lot of theory we just did here. In the next video, we're going to do some examples and hopefully see how this works in practice. So, thank you.